This video we're going to be talking about a distribution that is fairly well known. It's known as the binomial distribution. And the very first thing we're going to talk about when we're talking about this distribution is the notion of success. What we're going to be doing is we're going to be running a certain trial over and over and over again, and the chances of success each time are going to be exactly the same as all the other times. We're going to allow for the whole discussion a lowercase p to equal the probability of success on any given trial. And it's easy to do some examples to illustrate this. Flip a coin. The probability of getting heads is 1/2. So suppose we do this. Suppose I say success equals getting heads. Then the probability equals 0.5. And we could flip the coin over and over and over again. It doesn't matter how many times we flip the coin. Every new time I go to flip it, it's still going to be a chance of 0.5 that it comes up to be heads. So this is an example. That little p will stay 0.5 throughout the whole experiment. Roll a single die. Suppose success to you is getting a 6. You want the highest score for some reason. Well, the probability of any one number on one roll of a die is 1 out of 6. Another one where these seem to come up a lot are multiple choice exams. So suppose you have one where you have 5 choices for each question. So for example, I would have, say on question number 1, I would have A, B, C, D, and E to choose from. And chances are, if you have a multiple choice test, all the questions will have 5 choices to choose from, but only one correct answer. So what's the probability of success here if you guess? The lowercase p in this case will be 1 out of 5, one correct choice out of 5 of them. Now I can talk about a binomial experiment. All right, basically a binomial experiment is something where we do a task and run it over and over and over again for a fixed number of trials. So let's start with number 1. Each time you run the trial, you only have 2 possible outcomes. Each trial is independent from all the other ones. we run the same trial over and over again. And P is always the probability of success for any trial. As an example, let's flip a coin twice this time. Now, when we look at what's the probability of getting heads and heads, heads followed by heads. Well, to do this, I would probably want to have available to me the sample space for this. And we've done this before. Heads, heads is one of the outcomes. But then we have heads, tails, tails, heads, and then finally tails, tails. So as we look at these, we can see that HH is only 1 out of 4. But there's another way to do this. If you'll remember, let me get out of here for a second. If A and B are independent events, so if they're independent events, then the probability of A and B is the probability of A times the probability of B. So I want to do this problem up here in a different way. If I go, the probability of HH is the same as the probability of H on first coin and the probability of H on the second coin. And I didn't put the word that I want there. I wanted and H on the second. I can break that up to the probability of H on the first coin times the probability of H on the second coin. And the probability of each of those is 0.5. So that's going to be 0.5 times 0.5, which you'll see is 0.25. So I'm able to get this probability without having to look at the sample space. I can get it just based on the problem itself. I'm not going to bother with the sample space this time. The probability of 3 heads in a row, you're going to have a 0.5 probability on the first heads times a 0.5, which is the probability on the second heads. Finally, 0.5 for the third heads. And that equals 0.125. Or if you're doing it with fractions, that equals 1 over 8. Next, let's roll 2 dice. So what's the probability of the first dice coming up a 3 and then the second dice coming up 3? Well, on the first dice, to get any one number, the probability is 1 out of 6. So there's the first die, I guess, and here is the second one. And you end up with 1 out of 36. And you'll remember when I did looking at the total number of outcomes for rolling 2 dice, there were 36 outcomes total. So that would be a painful sample space to try to recreate every time. I think this is far more desirable. Now let's roll 3 dice. Now, this is no different than if I had rolled a die, and then another die, and then the third die. The way you toss them is not the problem here. So we can still think of there being a first die, a second die, and a third die. Well, what if I want the probability of 3 threes in a row? Well, on the first die, your probability of getting a 3 is 1/6. On the next one, same thing. See, that's the deal. This little lowercase p, let me put it over here so I can remind you. The chance of success on any one trial is 1/6. And you'll find that this is 1 out of 216. In fact, if you were to try to create the sample space for this, you would have a total of 216 items in it. Next, let's have a bag contains 5 blue marbles, 3 red marbles, and 1 green marble. Now, what I'm going to say is, let's first tell you what you're going to do. Reach in and grab one of these marbles at random. Now, what you can do is imagine that a game is being played here. And if money is involved in this game, then almost certainly you would get no money for drawing a blue marble, since they're the ones that are there the most. Now, there may be a payout of some kind for the red marbles, but the payout is really going to be the biggest for the 1 green marble, since that's the hardest one to get. So what I'm going to do is what I consider success here will be the green marble. And so, with that said, my lowercase p equals 1/9. If I keep doing this game over and over again, my chance of getting the green marble is 1/9 every new time I play the game. So with that said, suppose the game I just mentioned here is played 3 times in a row. And not only that, we're putting the marble back, so I'm going to call it with replacement. If you recall, that means that each time you play the game, it's back to its starting state. That's how we maintain the independence of the individual trials. So what if I want to do the probability? Notice that I'm using for the probability, a general probability, I'm using a capital P. The lowercase p is strictly for the binomial probability of each trial. It is probably an undesirable notation for sure, but unfortunately it is absolutely standard. And so if I try to choose any other letter, it's not going to match any book in the world. So we're stuck with these two things. So I will try to remind you as I do them when I'm doing a capital, or at least when I'm doing a lowercase, I'll try to remind you. So now, what if we wanted to do 3 greens in a row with this game? So once again, you have the first marble, the second marble, and the third marble. So on the first one, to get a green is 1 out of 9. Second is also 1 out of 9. And the third one is also 1 out of 9. Recall that when you multiply these across, 1 times 1 times 1 gives you the 1, and then 9 times 9 times 9 is 729. Let's say a friend wants to have 4 children. What is the probability that these 4 children will be all girls? Well, we take a look at each one of them. For the first one to be a girl, the probability is 1/2. For the second one to be a girl, the probability is also 1/2. The third one also has to be 1/2, and the fourth one has to be 1/2, for a total of 1 out of 16. What this means also is that the sample space has 16 items in it. Similarly, the probability of having all boys is also going to be 1/16. Part and parcel with success is failure. So if the probability of success is P, then the probability of failure is 1 minus P. Now, whatever is considered successful doesn't necessarily have to be beneficial. It just needs to be convenient for the problem. So in those things where I'm playing the dice game, suppose I roll a die, and if my probability of getting any one given number is 1/6, then the probability that I don't get that given number is 5 out of 6. Let's take a 5-question multiple choice quiz. Furthermore, each question has 4 choices. But only one correct response. So if you want to, you could probably think of it as having choices A, B, C, and D. Now let's say you go to this quiz and you guess on every question. What's the probability you're going to get them all right? So this is unusual. Let's say I use the letter C for correct and the letter W for wrong. Maybe not, I take it back. C for correct, I'll use the letter I for incorrect. So this is what you want to happen. You want to know the probability of getting the first one correct, the second one correct, third, fourth, and fifth. And just as before, we can break that up because since you're guessing, there is no relationship between the questions. They're all independent of each other. So what we have then is the probability of any one success is going to be 1 out of 4, since there's 4 choices but only 1 correct response. And you need this to occur for question 1, question 2, question 3, question 4, and question 5. Now, I guess I could multiply them all together. Let me see what we have. 16 times 16 is 256. I think it's 1 over 1,024. Feel free to go to the decimals if you should want to. More likely, let's see what this one is here. What about all of them incorrect? So what if we have 5 that we got wrong in a row? Move this up. Well, now the probability is going to be more, because the probability of getting any one question incorrect is 3 out of 4. So now I'm going to have 3 out of 4 times 3 out of 4. So I have to get all of these wrong. And there's what I have for my final. Well, let me multiply it out. I think it's 243 over 1,024. So just as an estimate here, this here is about 0.1%, and this here is about 24%. So as you can see, you have a much higher chance of getting all of them wrong than all of them correct. Now, what we might be interested in doing for this kind of a question is the following. I might want to let x equal the number of correct responses. So there's 5 questions on this test. That means the only values that x can take are 0, 1, 2, 3, 4, and 5. The probability of none of them is the first. This would be getting 0 on the test, which we got up there. And then down here, we have the probability of getting it perfectly. Now in here is a little more complicated. This problem is probably a little beyond what I want to task you with for these kinds of problems. To fill in these things requires formulas that I'm not going to give. But this material is still useful, and we should know the following about this. When you add everything up, this column here, which is the probability of x, should add up to 1,024 over 1,024. Now what I've done so far is I've got 243 plus 1. I have 244 of those things figured out. Why are these so complicated? Well, the problem is this. Here's what could happen. When you go to take a test, let's take a look where you get just one correct. So you have something like this. Let me call this x equals 1. So there is, but that's only 1. There's more. Like this is also getting exactly 1 correct. See how that C is moving through there? And then I even have one last one. So what we see here is I have a total of 5 ways of getting one right. So what we have here then is, so let's take, here I'm going to get, there's 5 of these. Let's take any one of them. They're all going to have the same probability of occurring. All you got to do is know the probability of 1. So let's take the first one as my probability here. Then I can break it up. I get the first question correct. That means I had a 1 out of 4 probability. But for the rest of them, I get them all wrong. That's 3 out of 4. So this is a total of 81 out of 1,024. Then let me go ahead and erase this. What you would have happen then is to put an answer here, I've got to multiply by 5 because there's 5 ways to make this happen. So you got the 5 ways times the 81 over 1024. It's just like multiplying 5 times 81. So in fact, you'll get 405 out of 1024. Like I said, this is a little beyond what I want you to be able to do. And 2 of them is even crazier. If I have 2 C's and 3 I's, there's actually 10 ways of doing that. And then it's the same complication if I go for 3. 4 is a little less complicated, but the problem is these require some counting techniques that we're not really going to do in the course. So I'm going to make the examples that I do a little bit on the smaller side so that you can create one of these probability distributions given the game or situation that I put you in. Consider flipping a coin twice. Now, let success is going to be heads. That means the lowercase p is equal to 1/2 or 0.5, whichever. I'm probably going to do decimals because I think it'll be easier. So we have that. Now, how many possible, well, let's see, I flip a coin twice. How many possible heads can we have? So I'm going to let x equal the number of heads. So when we go through these, well, you can certainly have no heads, you can have 1 heads, or you can have 2 heads. Now let's take a look at the probability of 0 or 2 heads. So the probability of no heads means that I got a tail on the first try and I got a tail on the second try. So the probability there is 1/4. I'm going to do it in terms of decimals. Now the probability of getting 2 is also 0.25 because that's really the probability of getting no tails, which is an identical thing to do. Now here's where you can come in and sort of help yourself. You could certainly write the sample space as you want. However, note that this thing adds up to 1. And right now I've used a 0.25 here and I've used 0.25 here. That's a total of 0.5 that I've used up. That must mean that 1 heads is 0.5. And indeed, I'll prove it to you. So you can see the probability of 1 head are these 2 things in the middle. That's 2 out of 4 of them satisfy having 1 heads. So what I'm going to do is, there's not really any homework problems that I could find to put on this thing. What I'm going to do instead is I'm going to give you a situation, a binomial situation, and expect you to fill out one of these probability distributions. I think that's the kind of question I'm going to ask. So with that in mind, I'm going to do a few examples. Let's flip a coin 3 times. Or flip 3 coins. What does the probability distribution look like for that? So as before, I'm going to let success equal heads. So on any individual trial, we know that lowercase p is 0.5. I think I'll go with decimals for this. And I'm going to let the variable stand for the number of heads. This is typical. Whatever you want to be, X is going to be the things usually that you want it to be successful. So when I put out my possibilities now, I have 0, 1, 2, and 3 possibilities for heads. The probability of each of these, let me see what I can do. Usually the extremes, the 0 and the 3, are really easy. So let's take a look at the probability of 0 heads. That means you got a tail on the first one. Let me go to decimals. I didn't want to do that. So you got a tail on the first one, a tail on the second one, and a tail on the third one. Altogether is you get 0.125. Now, on the other hand, the probability of getting 3 heads is the same as the probability of getting 3 tails. It's going to have exactly the same probability. Now remember, down here, this has to add up to 1. If I take 0.125 and I take 0.125 again, add them together, I get 0.25. That means in this gap here is 0.75. And it's evenly split among these two rows. The reason why is because getting 1 heads is the same as getting 2 tails. So whatever 1 heads is the same as 2 tails, so I could say this is the 2 tails range, and this is the 1 tails row. So you have whatever I get, I'm going to get the exact same thing in here. So I told you that 0.75 was in the whole thing. So knowing a little bit about the properties of a probability distribution helps us do this. Now, this is also the kind of a problem where you might want to check it. And counting, I haven't talked much about counting, and we're not going to do a lot of it, but you should be able to do some basic counting. So what I'm going to do is the 3 flips, I'm going to show you how to count them out. So on our first flip could look something like this. This is flip 1. First coin, whatever you want to call it. That could have been either heads. This line is too long. Let me make it shorter. Tails. Then on the second flip, you can also do heads or tails. I recommend structuring it the same way every time you do it. So notice I'm putting an H first and the T underneath of it. If you start mixing them around, I have a feeling that's not going to be so good. And this is my third flip. Now what you want to be able to do is trace and remember how you got to these endpoints. So if you look, in order to get to this spot up here, I had to have 3 heads in a row. So that's the outcome of heads, heads, heads. Here then, I have heads, heads, tails. Then let me continue. So for this one, I have heads, tails, heads. Now let's go some more. Heads, tails, tails. If you notice, what I've done here is counted out all the ways where the first coin happened to be heads. And all these down here are going to be where the first coin are all tails. So let's go here. We have tails, heads, heads. And then I have tails, heads, tails. Tails, tails, heads. And then, of course, 3 tails is the last one. So if you look at this, you can see there's 8 possible outcomes. Here, to get all heads, the probability of that was 1 out of 8, or 0.125. Same thing down here. Each of these, this section in here, if you look here, if I take a look at I have HHT and HTH, THH. So if I take this guy here, and this guy here, those 3 things there add up to 3 out of 8. And then, of course, these remaining ones are also 3 out of 8 when you put those together. So that's how I get the 0.375 for them. So you can kind of use logic to get these, and a little bit of thought will tell you that 1 and 2 had to be the same. That won't be true for everything, though. That'll be true whenever you have something where the chance of success is identical to the chance of failure. That's a 50-50 shot. But in those cases where, like, say you're taking the multiple choice test, this is not going to work like that, because your chances of failure are much higher than your chances of success on any trial. Pick a card. Success will be getting diamond. So the probability of that happening is 13 out of 52. Or even better yet, 0.25 may be desirable. I'll wait until I'm into the problem before I decide what version I want. What I would like to do is play this game, but put the card back each time. So we're going to pick a card repeatedly with replacement. Let's do 4 cards. So with replacement, you know what that means, we've explained it, is that each time you're putting the card back, reshuffling the deck, and picking another card again. So that's what replacement means. Now, I would like to keep the number of hearts, I'm sorry, the number of diamonds. So X equals the number of diamonds. So if you play this 4 times, that means that X can go anywhere from 0 to 5. I don't know why I said that. 0 to 4. You could certainly have no diamonds, or you could have all diamonds. With replacement means that each draw of the deck is independent from all the other ones. So let's start with 0. What is the probability of getting no diamonds? So what would you have to have? I'm going to use letter D for diamonds, and I guess I'll use the letter N for not diamond. So 0, X equals 0, means that we're talking about the probability of getting no diamond, no diamond, no diamond, and no diamond for all 4 cards. Well, to get no diamond, the probability here, you can look at it in a bunch of different ways, but the probability of failure here is 0.75. So this is a failure 4 times over. So an easy way to do that is 0.75 raised to the 4th power. I'm going to round to 4 decimal places, but you probably shouldn't if you want the numbers to work out exactly. I'm not exactly sure I don't know if it'll let me copy this in here or not. Let's see what happens. This is probably not going to be great, but I'm going to see what happens when I try to put it in this table. Well, I guess it didn't work out so badly. Now, let's take a look at the other extreme. X equals, this time you got all diamonds. So it's the probability of diamond, 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 diamond. There's only 4 of them. So you'd had to get diamond on the first card, so that's a 0.25. A diamond on the second card, which is also a 0.25. Third card, and finally the 4th card. You can see the probability of this is going to be less than this one here for sure. Let me go to the calculator and do 0.25 raised to the 4th power. So I have those 2 down. How do I do the rest of them? So this is going to add up to be 1. We know that. What about, see, some of these are easier to count than the other ones. If I take a look at the probability of getting one diamond, then look what I have. So let's do the probability of x equals 1 is one diamond. So what are my situations that I have? For one diamond, I can do diamond, no diamond, no diamond, no diamond. But then the diamond could appear in the second slot instead. See, these are easy to count all these possibilities. It could then occur in the third spot. And then finally, it could occur in the fourth spot. Each of these will have the same probability. I'll take the very first one here. This case, the diamond comes first, that's 0.25, followed by 1, 2, 3 at 0.75. Let's go ahead and pull up the calculator. Now it's also going to be easy to do x equals 3. Let me go down here. And I forgot something actually. These are 4 equal things, so I go like this. Times, I don't want to put, I'll put the word multiply by 4. So that's what I meant here. I should have had, instead of that whole thing, since there's 4 of them, I need to have 4 times all of that. So I need to take my answer and multiply it by 4. Now let me go back to the 3. Means that we're going to have 3 diamonds and 1 non-diamond. So it could look something like this, or this. The reason why this is easy to do is because there's only 4 possibilities here. Each of these has exactly the same probability. Now I have to multiply by 4 because I have 4 of these. But each one of these will have exactly the same probability. The probability of getting a diamond is 0.25. The next one being a diamond is also 0.25. 0.25. So there's my 3 diamonds right there. And then we've got to put, for the last one being a non-diamond, is 0.75. Now this case here where we have 2 diamonds with 2 non-diamonds, there's actually going to be 6 possible outcomes for them, but I don't need to know all that. I know that this whole thing adds up to 1. So that tells me that if I start adding these up and whatever I get for these 4, subtract it from 1, then that's going to be what's left over. So let's go ahead and do that. It always seems to go over exactly where I want to go. So I'm going to start with the number 1 and start subtracting stuff. So I'm going to subtract, I'll start with this up here. 0.316400625. Enter. Now I'm going to subtract this 0.421875. Then I'm going to go down here and subtract 0.0. Well, you get the idea. And then I'm finally going to subtract this from it. And there's my answer. It makes sense too. The numbers, the percentage is getting lower as you go down, and that certainly looks like it doesn't look inappropriate to be there, that's for sure. So there's your frequency distribution for my particular problem that I made up. Now we're going to use this for a couple of things. We have two measures. One of them is called the mean, and it has the letter mu, the Greek letter mu, and you do n times, well, let me be a little more careful here, n times your lowercase p. N is the number of trials that you run. And then we have the standard deviation. That is sigma. That's a lowercase sigma. That's the Greek, that's their version of S. That's the square root of n times p, lowercase p, 1 minus that lowercase p. That's the standard deviation. So if I want to do it for that previous problem that we had, we had n is equal to 4, and the probability of success was 0.25. So the mean is going to be 4 times 0.25, which equals 1. What this means is that if I do this game 4 times, if my probability is 1/4 on each time I try, doesn't it make sense that I would have exactly one card that would be diamonds? Because I would expect only one success. And the standard deviation for the probability of success was 0.25, and then the probability of failure was 0.75. Let's go ahead and do this on the calculator. Where's my square root? This is a little bit odd. I want to show you something. If you look where my mouse pointer is at, most calculators do not put a little 2 up there. Although there is understood to be a 2 there, they mostly don't put that. So don't let that frighten you if you see something like that on your calculator. Although I don't believe I'm not sure I know of any calculator that actually does that. But anyways, I think you press it after you put the numbers in. So we'll start with 4 times 0.25. It did not do what I wanted. Let's backspace here. 0.25. And then times 0.75. Now let's see if it lets me take the square root of that. There it is. So to 4 decimal places, I got 0.8660. These aren't that big of a deal right now, but they'll be important later on when we start doing heavier questions with these kinds of things.